This video is going to introduce the concept of thermochemistry. Now, thermochemistry is about energy, so I wanted to start by talking about kinetic versus potential energy. So kinetic energy is energy of motion. So molecules contain kinetic energy because they move around. Potential energy is energy based on position. And so if you think about throwing a ball up in the air and having it fall back down to the earth, because of gravity, we know that it takes energy to throw a ball up into the air. So when it reaches, as it's moving up, it has kinetic energy. The higher it travels, the more potential energy it has. So the kinetic energy will go down, it'll start to slow down, and that kinetic energy will get converted into potential energy. And the reason it has potential energy when it's high off the ground is because we know if we let it go, due to gravity, it will fall back to the earth. And so it's the same as this hill with the little bicycle guy on it. He has to put in kinetic energy. He's moving on the left-hand side. And as he goes up that hill, he starts to slow down. And at the top of the hill, he has the highest potential energy. And he's stopped, and so his kinetic energy is at 0. And then he can travel down the hill, and that potential energy will again get converted back into kinetic energy as he goes faster and faster. At the bottom of the hill, and when the ball reaches the earth, it has no potential energy because we know that it will stop at the bottom. Now, another thing that we need to do is we need to define system and surroundings. And so we're going to look at various reactions going on. And so if we have a reaction going on inside this flask, the system is usually considered the reaction, and even the surroundings are sort of everything else. And so the system, we can define the system in different ways, but often the system for us is simply the reaction that takes place, and the surroundings is basically everything else. And so the system, even if the reaction takes place in water, if the water molecules are not a part of the reaction, which often they are not, they're considered the surroundings. And so we're going to talk about that. But the reason why we need to define system and surroundings, and we care about that, is because the energy within this whole universe flows from the system to the surroundings or the other way. And so we're going to talk about energy going from the system to the surroundings or back, and we might talk about heat going from the system to the surroundings. And so we need to understand what those concepts mean. So we're going to start talking about enthalpy, and this is related to a lab that you did. So enthalpy is the heat associated with a process at constant pressure. It's abbreviated with a capital H, enthalpy. And we can measure changes in enthalpy as reactants convert to products. And so this idea of endothermic versus exothermic refers to enthalpy and the direction in which heat flows. And so on the left we see an endothermic process or an endothermic reaction where the system or the reaction needs heat in order to occur, and heat has to go into the system from the surroundings. So endo means in and therm means heat. So an endothermic reaction is one that needs heat. It's going to absorb heat from the surroundings, and that's going to cause the surroundings to get cold. On the right is an exothermic reaction. So exo means out and therm means heat. And so an exothermic reaction is one that generates heat that it releases to the surroundings, in which case the surroundings get hot. What you see here is an enthalpy diagram where enthalpy, remember, is abbreviated capital H. That is shown on a vertical scale here. And so in this case, an endothermic reaction you would see on the left where the reactants have lower enthalpy than the products, and they have to gain heat in order to go from reactants to products, in order for the reaction to proceed. So on the left is endothermic. The products have more enthalpy than the reactants, and therefore heat must be added to the system. It is absorbed from the surroundings. Delta H, that is the enthalpy of the products minus the enthalpy of the reactants, is a positive value. On the right-hand side, where the reactants are shown to have higher enthalpy than the products, this would be an exothermic process. The products have less enthalpy than the reactants, and so that means that there's going to be excess heat at the end that is released to the system. Oh, released to the surroundings is what it says. Should say. Excess heat is released to the surroundings by the system, and then delta H would be negative here. So delta H is the enthalpy of the products minus the enthalpy of the reactants. The enthalpy of the products is a lower value, so delta H would be negative. Solving a solute in the solvent, and then you're making a solution. So when we think about this dissolution process, it's helpful to think about it as a series of steps. So we're going to separate the solute particles, which are shown here in purple. We're going to separate the solvent particles, which are shown here in blue. And then we're going to bring them together in step 3 and form these solute-solvent interactions where we form the solution phase. So when we think about what's happening here, this first step, separating solute particles, always requires energy because the solute particles are attracted to each other. Separating solvent also requires energy because the solvent particles are attracted to each other. When we bring them together, however, that always releases energy. It supplies energy. So that's sort of our payoff phase of this process. So if we divide this up into 3 different delta H's, delta H1 we know is going to require heat, require enthalpy, so that one's going to be positive. The second one will also be positive. The third one will be negative. And the question is, when we add them all up, will we get an overall value that is positive or negative? So if we look at this on an enthalpy diagram, here step 1 is what I've shown on the left-hand side, and there's a little cartoon of it up on the right-hand side that we've already seen. When we go from the solvent to the solute, we add those together, we're going to separate the solute particles from each other. We know it's going to require energy, so we know it's positive, and so we know that's an endothermic step. It's going to go up. We know the second step is also endothermic because we need to separate the solvent particles from each other. And then finally, when we bring them together, that's going to be our sort of, and maybe it pays off a lot of energy. Maybe we get a really negative delta H back. So the formation of the solute-solvent interactions releases or supplies energy. And so that's the red arrow that you see on the right-hand side. And so in this case, when you add up all 3 of these, the overall reaction that you feel with your hand would be shown here. The net reaction in this example is exothermic. And that's what you observe. In this case, if it was an exothermic reaction, the test tube would get hot because the energy that's given off is given off to the surroundings, and you feel that energy given off, that heat. That's the overall that we see. This enthalpy payoff, this delta H3, is greater than the cost when you add delta H1 and delta H2. And that excess heat is released to the surroundings. Now if we contrast that with an endothermic process, then they all, 1 and 2 still require enthalpy and 3 still releases enthalpy. But in an endothermic process, the enthalpy cost is greater than the payoff, and so the net reaction at the end is still endothermic. So the heat that's required is absorbed from the surroundings and they get cold. This is just another example of some processes that are extremely exothermic versus endothermic. And then here's some practice problems that we're going to do next. So here we're going to consider the following diagram for the dissolving of potassium bromide. So here, this is an enthalpy diagram where enthalpy is shown on a vertical scale, where anything on the low side of that scale has a relatively lower enthalpy than anything at the high end of that scale. So in this particular diagram, you can see that KBr solid has less enthalpy than the separated aqueous ions K plus and Br minus. So the first question, is this reaction endothermic or exothermic? So remember, for an endothermic reaction, Heat has to go into that reaction because it needs more enthalpy to go from the reactants to the products. It's going up in enthalpy, so it has to gain that enthalpy from the surroundings. Heat in, right? And exothermic means heat out. That means that it falls in enthalpy, which means it has extra heat at the end. So in this case, you can see that the reactant, KBr, has lower enthalpy than the products, which means that this is an endothermic reaction. Heat must go in order for it to get up that incline, right? So delta H is the enthalpy of the products minus the enthalpy of the reactants. In this case, delta H in this case is positive, and you can also kind of see from the diagram that it has to gain enthalpy, gain heat in order to get up this this wall that it has to get over, right? Part B, if you dissolved KBr in water, would the test tube get hot or cold? So you know this from lab. If this is an endothermic process, that means that heat has to go into the reaction to make it occur, which means the heat has to be stolen or absorbed from the surroundings, which means the surroundings, which is the test tube and the water, get cold, right? Heat goes in, so the surroundings get cold. That says Qn, which means it gets cold. Part C, in this case, which is likely to be greater? The energy cost of separating the ions and separating the solvent, or the energy payoff when the ions and the water molecules interact favorably and come together? So this is related to what we talked about in class. When you dissolve substances, you think about it in 3 steps. One is the separation of the solute, and that's shown with this orange arrow where KBr gets separated to form K plus and Br minus, and that always costs energy. That's always endothermic. And then we also have to separate the solvent particles to make space for the solute particles to be mixed in together. And so this gray arrow is showing you that you also have to separate solvent water molecules from each other, which also costs enthalpy. That's also endothermic. But then there's always a payoff, and so you always get some energy or enthalpy back when they come together. Okay, so that's the next arrow we're going to show. In this case, however, the payoff is not as significant as the cost, and you know that because there's still some extra enthalpy that has to go in. There's still a small amount of enthalpy, a small amount of heat that has to be absorbed from the surroundings, represented by this green arrow. So in this case, the cost is more than the payoff. And you know that because it's endothermic. So the cost is greater. That's why I'm underlining that in green. Number 2, consider the following processes to determine if they are endothermic or exothermic, and the sign of delta H. When concentrated HCl is added to water, the solution gets hot. So the information that you have there that will help you answer this question is the temperature change. The solution gets hot. That is always true for an exothermic process. The excess heat is released to the surroundings, which is why they get hot. So that's exothermic. Delta H is negative. Water is boiled in a pot on the stove and converted to steam. Now there's a couple of things here that would help you answer this question. One is that this is a phase change. We're converting liquid water into gaseous water or steam. And we learned in class that phase change is going from the liquid to the gas. That is an endothermic process. So I know from the phase change description that this is endothermic, liquid to gas. You also know that water is boiled in a pot on the stove. So this whole idea of having a pot on the stove means you have to put heat into it, which also implies that it is endothermic. So liquid going to a gas, that's always endothermic. Delta H is positive. And also boiled in a pot on the stove. That means that we have to add heat. So that's 2 pieces of information that both tell you this is endothermic. Part C, when a salt is dissolved in water, the solution temperature changes from 24.5 degrees to 31.2 degrees. So the only information you have there is the temperature change. The temperature increases, which means the solution gets hotter. Those are the surroundings. That means it's exothermic, and delta H is negative.